All right. Hello, everybody. Let's start with our next talk. Ákos Magyar is here
From the
to
University.
talk to us
Yeah. From the University of Georgia.
from the University of Georgia.
Okay. So it has a long title, but during the talk, I will try to explain it. So one can give a title something like almost prime. In programming of what degree forms. In many variables. Let me abbreviate at least variables. Okay. So let me start with some background. Is it readable from the back? Okay, so there were a few results for integer solutions of odd degree systems, and just to define some setup. So let's say F is a family of integer polynomials, F1 and R. Fi is in, say, X variables, and it's a form, so homogeneous, and odd degree less than equal D. So all of the forms has degree less than equal than some fixed D. And then we look at, say, the integer 0 set. Let's say we have Z. So these X is in Z to the S, where all of these Fi's vanish. J, let's J up. So it was shown that, and this was a number of results, namely Birch or Davenport for D equals 3 for a single form, then Birch for a general system, and then essentially strengthened by Schmidt, which says that without any additional assumption, if the number of variables is sufficiently large with respect to the degree and number of equations, there exists an non-trivial integer solution. The strongest results of this type, which I will recall, is due to Schmidt. Let me know when I'm writing too long, but maybe I try to squeeze. And I call this theorem S. So that's Schmidt, 95. Oh, 85, sorry. And let's say it's not just says that there are solutions, but there are a lot of solutions. So let's say you count integer solutions in a box, say negative capital N, N to the S, such that Fx equals 0, meaning that all polynomials vanish at X. And this number is bigger than a constant depending on F, positive constant, times N to the S, that would be just without any restriction, minus some in the exponent, minus some constant that just depend on the degree and number of polynomials. Okay, so this is essentially stronger than just having a non-singular solution, but we see this only makes sense if S is larger than, for example, this constant, because there is already a solution. So for small s, just one solution would be enough. So this is really a statement when S is large, and also interesting, of course, when M capital N goes to infinity. So what I would like to talk about today is strengthening this result by restricting the coordinates into an arithmetic set. Would be too ambitious to say restricting the coordinates into the primes, but one can prove something weaker, restricting the coordinates into almost prime, where the notion of almost prime is a little bit different than the usual notion. So that would be the main result I would like to talk about. Maybe this is good, or maybe this is better. So let me I don't want to write here, so let me clear this if this statement is clear. Okay. Maybe okay. So I won't be. So the setup is the same. So we have a system F, F1, Fr, with the same conditions. And so then the difference is that there exists a constant, depending only on the system, a positive constant, such that the number of solutions x in minus n to the s, such that each xi is of the form some yi times pi, where the absolute value of yi is less than equal than the fixed constant yf, and pi is a prime. And still solution. Then we would have a similar result as Schmidt. It's bigger than equal than a positive constant, depending on f, times n to the s minus b, where b is some constant, which depends only on the parameters degree and the number of equations. And since we restrict pi to the primes, I mean, wouldn't really matter, because if I put -1, that would absorb this factor, just to indicate that we are eventually counting prime solutions that would be log n to the s. Of course, in the statement that log n to the s doesn't really matter. Now, a couple of remarks here. So I call this theorem M, Main's theorem. So there is one thing here, that we don't require the yi's to be non-zero. Now you would say if all yi equal to 0, we would get a trivial, so we would just have trivial solutions. But if many coordinate 0, then we get less solutions than this one. So in fact, what we prove here that there exists an index set J subset of S, whose cardinality is also just bounded by a constant. And actually, you can essentially make it to be the same as B, but let's say J0 BI, such that yi is not 0 for all I, not in this exceptional set of coordinate J. Okay, so with the exception of a bounded number of coordinates, indeed, the rest of the coordinates are indeed almost primes. And you cannot avoid this condition because some of the equations could be just, for example, x1 equals 0, x2 equals 0, x1 cube equals 0, or some combination of the equation can lead to that. So this is necessary. For example, you can have f1x equal x1, and then this should force the first coordinate to be 0. Also, we need the yi's. It would be overly ambitious to try to find prime solutions directly. For example, so these are some necessary conditions. For example, you can take an equation f1x, something like x1 minus 4x2 plus minus 1 to the s minus 1 or to the s minus 1xs. And for this, if you set this equal to 0, even if you set any number of coordinates 0, you still won't have a prime solution of this equation. Because you look at the first one, 0 coordinate, divide by a power of 4, and that prime should be divisible by 4. So you need this kind of scaling variables yi. And on this equation, it's easy to see if you scale this equation, then of course you can have many prime solutions. So if you set for this equation yi to be equal to 4 to the s minus I, and then you look at solutions xi, 4 to the s minus I times, let's say, pi, then you get the equation just something like sum of minus 1 to the I minus 1 pi, I equal 1 to s equals 0, and it is known that this equation has many solutions, asymptotic number of solutions. So the idea of the proof is to construct carefully these yi's so that you can apply a theorem. There are a number of theorems about prime solutions of Diophantine systems. So let me continue with eventually what type of theorems we want to use after constructing the scaling. So I guess I should clear this too. Does it make sense what the statement is? Any question? Okay. So let's say, so the main tool what we use is certain type of theorems for certain Diophantine systems, which can give an asymptotic form of the number of solutions where each variable is a prime. So let's just say prime solutions. Okay. So that's also, there were somewhat recently a number of results about that. Roughly speaking, this theorem says that if, so let's say we will eventually transform the original system to a new system. So let's say we have a system of form G equals G1, GR, but we can also group into blocks of degree L. So maybe we can also write this as G1, G2, GD, where GL is the block of polynomials of degree L. And roughly speaking, the theorem says if each block has high enough rank with respect to the degree and number of equations, this is the so-called Birch rank, and then the system has a local non-singular unique solutions for each prime, then one can asymptotically count the number of prime solutions. So roughly speaking, or a little bit more precisely, so we have two conditions needed to have this theorem. If the so-called Birch rank, which maybe I will define of each block, is large, bigger than some function of the number of equations and the degree for each L, and if Gx equals 0 has a non-singular solution in Zp cross, so Zp minus 0 to the S for each prime, including R among the reals. Then the following quantity, and let's say instead of primes, we look at as usual the weighted number of integer solutions with von Mangold weights. Mg of n, which is defined as the number of integer solutions in the box. Well, not quite. This is, let me write it a little bit differently, which is defined over the sum of, can you see this? Yeah. Integers in the box of size n, which are solutions, and you multiply it with the von Mangold function of the coordinates. And this would be equal, asymptotically, to some constant depending on g times n to the s minus the total degree of the system. And that is what one expects from the circle method. So d of g is the sum of the degrees of the gi's equal 1 to r. And sigma g is positive if this condition holds. Now we are looking at primes, so locally, periodically, you need a solution whose coordinates, which are periodic units. Okay, because okay, so this type of theorems were obtained by Brian Cook and myself back in 2014, and then Yamagishi extended in a series of papers, I think 18 to 22, and then Liu, Zhao, and CA proved quantitatively stronger results for the number of variables for the rank condition needed. That was more recently 23, I think to 25, assuming the system is non-singular, which I don't think is that different than just a large rank condition. So this, I call it theorem P. This is what we want to prime theorem, what we want to eventually apply after working on our system, so that this result becomes applicable in the PI variables. Okay, so the bottom line is for high enough rank systems, and maybe I did not define yet the Birch rank. Essentially, for a Diophantine system, it's an algebraic geometric notion. It is the codimension, the so-called singular variety, when the rank of the Jacobian drops over C. Where for the Birch rank of a linear form is different. It is simply the number of non-zero coefficients of a linear form. And for a family of linear form, you take all possible linear combinations, look at the Birch rank of those linear combinations, take the mean. So large Birch rank means that roughly, and this linear part of the system will be quite important in what follows. Okay, so let me just very roughly describe the idea of CRMM, the main result. So that this, any questions about this part? Okay. So the idea of the proof, which I will detail in the remaining time, so we start with an arbitrary system F. Oops. Odd degree system. Every system we work with will be consist of polynomials or forms, homogeneous polynomials, odd degree. And then we do what is called something like a regularization, or a version of a regularity lemma for polynomials. And we arrive to a system G which has large rank. Knowing what notion of large rank, that's technically a little bit difficult because we arrive at the so-called Schmidt notion of large rank, and then we have to move between the Schmidt and Wirth notion. But fortunately, there were some recent results by Lampert and Bailey, which shows that these notions are, these ranks are equivalent up to a fixed constant, depending on the dimension. And then we do a little bit of cleanup, and which will be needed later. So that's where we will set some coordinates to be equal to 0. So to get a system which is better suited to finding non-singular solutions. And then we will do the scaling. So we will construct the y's, and instead of the gx, we will have a yi times xi, considering as a new system of xi's, for which we will be able to find non-singular solutions. So here, in this process, this scaling removes local periodic abstractions. Remove. And then applying CRFT. And then we find a lot of prime solutions of the scale system, which is our theorem. Okay, so this gy, of P is simply G of Y1, P1, YS. So, what are these steps? The first step is what we call regularization. Now, this appeared in our paper, but before the infinite characteristic, in some papers in additive combinatorics. The idea is, okay, so the idea is if you define the, actually it's already appeared implicitly in Schmidt paper about counting number of integer solutions, although it wasn't given as a statement, but it was embedded in an inductive proof. So what does it say? So basically, we have starting from an arbitrary system of odd degree forms, less than equal degree d, and odd degree forms. And then this regularization gives us a new system gr prime, so some r prime form, but this is also odd degree. Less than equal than d. And then if we look at the blocks of G, now the so-called Schmidt rank or Schmidt invariant, then we have the following three properties. First of all, we don't increase the zero set, so V of G is contained in V of L. The second is that, and I will define in a second what is the Schmidt rank, that the Schmidt rank of any block will be, okay, bigger. Maybe here I should say that we also fix the so-called increasing function of V and R going to infinity, sometimes called the gross function. These all appear in all forms of the regularity type lemma in graph theory and so on, that is bigger than equal than this prescribed function, but it's very important depending on the degree and number of forms of the new system. So it's very large, even though we generate, maybe this is a huge number, nevertheless the rank is bigger than any prescribed function evaluated at this number. So this means that this is a very high rank system for all L bigger than 1. For L equal 1, the linear forms, we cannot guarantee that. We can only guarantee it's a linear independent system, which is kind of trivial. You can just remove the linear forms, which are linear combination of the others without increasing the zero set. So here, G1 is linearly independent. And what is the Schmidt rank of a single form? If I guess many of you are familiar with that, but HF is the minimum of positive integers H such that you can write F as a sum of UI times VI, sum of product of forms, I equal 1 to H, where these are non-trivial, so the degree of UI and the degree of VI is at least 1. So, for example, if F is a power, then its Schmidt rank is 1, because you can write a product of just two functions. And then for the Schmidt rank of a whole block is the minimum of the Schmidt rank of any linear combinations. So the Schmidt rank of a block is large, means that any linear combination cannot be decomposed into a sum of at most H products, small sum of products of polynomials. So this is the first step. Use this regularization. So replace the system F with the system G. We didn't increase the zero set, so it would be enough to get a lower bound on the size of the zero set of the system G. And also, similarly as in graphs here, you need to do a little bit of cleanup. And here, in this theorem, you don't need a large number of variables. It's a little surprising, but you don't need it. Well, if you originally have a small number of variables, maybe you just get a linear system. Maybe you don't have any large rank forms remaining. But there is this problem that in the prime theorem, you need that these linear forms doesn't have a linear combination which depends just on one or two variables, because you wouldn't have prime solutions. So we need to make this system to have large rank, which means that any linear combination should depend on many coordinates. But the trick is, if one linear form or a linear combination of forms depends just say on 3 variables, you can just set those 3 variables equal to 0 and go to the subspace, because we allow a bounded number of variables to be 0, and on that subspace you remove the linear forms. And you can do this until no bad linear forms remain. So that's a sort of cleanup procedure, but for that you need already a large number of variables. There is another cleanup procedure needed, because eventually we need local p-adic solutions among the units. So we don't really want any of the coordinates to be 0. And one can do a preparation here. And I won't want to describe this formally, write it down, but it's something like, we look at the system G, and we look at its zero set about the complex numbers, so geometric zeros. And we look at the maximum irreducible components of that. And we don't want any of these irreducible components to be contained in a hyperplane xi equals 0. And that can be also managed by simply, if one of the irreducible components is contained in a coordinate hyperplane, then you restrict to that coordinate hyperplane and the codimension is reduced by 1. And you can do this until this won't happen and the number of coordinates you need is not bigger than the original codimensional variety of G, which is described by R prime equations. So after this, the codimension couldn't be bigger than R prime. So you remove another bounded number of coordinates, and then you can assume that no maximum irreducible component is contained in any coordinate hyperplane. So after doing all these restrictions, we have restricted the system a smaller subspace and remove some linear forms. So we get formally that another system G prime, but we will work with just that system from now on. So let's say we assume G has this extra properties. And if you look at some work on the graph regularity lemma, there after regularization also removed a bunch of small components and a bunch of low density parts and so on. So this cleanup type of thing is very natural to be applied with regularization. Okay, so the third step would be finding p-adic solutions. And then finding, so at this point, we have a system G such that each block has large rank. And it has a large rank in the sense of Schmidt, but as I mentioned, then it has large rank in the sense of Birch above C. So the codimension of the singular variety of these blocks is large. And then there is a theorem in algebraic geometry which is never stated, or it's very hard to find to be stated in this form, but it says that this Birch rank doesn't drop under mod P reduction, except for finite many primes. Okay, so so the next step is finding p-adic solutions. And there are two cases. The first case is large primes. And that means P is bigger than equal than some threshold, depending on the system. And now we can assume that the Birch rank of any block, GL, is large in the sense that large enough with respect to the number of degree and number of equations above Fp, which is the finite Fp bar, the closure of the finite field of P element. This is this mod P reduction theorem, P bigger than Pf, that this remains true. And then one can use exponential sum estimates to count solutions just above Fp, which are non-singular. Let's define V of G, Fp. This is just Fp, not Fp bar, is the number of x's, Fp to the s. Of course, s has changed, but let's call the remaining non-zero coordinates number of nodes to be s. Gx equals 0. And then, just by exponential sum estimates for large primes, using that the Birch rank is large, mod P, one can do basically a mod P version of the circle method, which is much easier than the original circle method, essentially by differencing to get that VGFP is as what one expects, which is P to the S minus R. So let's say we denote by the number of points GR, plus an error term, which is smaller. So this is just basically exponential sum estimates. But at the same time, we want to find solutions that with no coordinate equal to 0. But at the same argument gives you that VGFP intersection with any coordinate hyperplane that's equivalent to a S minus 1 dimensional space. So in that you can also find the solution, and that is bounded by S minus R minus 1. And finally, we also want non-singular solutions. So we want to remove all the singular solution, which is in the singular variety. but the singular variety has large codimension, so you can use a very basic algebraic estimate is bounded by p to the dimension of the variety. So let's call that Vg star Fp. So that's the singular, so the set of singular points where the rank of the Jacobian drops. And that is also, you can set it up, p to the s minus r minus 1, as by this assumption basically means that large. So if we put all this together, then we can find a solution which has all the nice properties in Fp, so there exists solutions, say F star in Fp to the s. None of the coordinates are equal to 0 and non-singular. So this is how large primes work. Okay, for small primes, we cannot quite do this, but we can do something which will be fine after some scaling. So, any questions? Oh, sorry. I mean, here you really need a Hensel lemma. Yeah, actually, not what we want. Yeah, so that is true, but we want eventually. So this can be lifted to a periodic solution by Hensel's lemma. And then we will have some, let's call it XP. And that would be indeed in ZP cross to the S and remains non-singular. So that's just the simplest case of Hensel's lemma. If mod P already you have a non-singular, no zero coordinates, then you just lift it up P squared and so on until you get a periodic solution. Okay, so for the small primes, neither this condition, neither this estimate is not very good because the primes are small and then maybe the Birch rank drops, so one has to argue. You see that? 10 minutes, so maybe I should hurry up very quickly. So for the small primes, what we have is we use the fact that the Birch rank over C, so we don't use finite fields of any block is large, but the Birch rank over 3, C and QP bar does not change because this is just a so-called base change. So this is large. And then we use two ideas to find solution. One is from Julia Brandes. So it says, since the codimension, this is essentially the codimension of the actually. Now this is a little bit of cheating, but there is also a theorem of Lampert that, and the whole codimension of the single variety of the whole system is also large, if that is true for each block. So that's another theorem of Lampert. This is called the rank drop lemma. It's a fact from algebraic geometry. It is true for characteristic 0 base field. So anyway, since this is large, so the singular variety has large codimension, then one can find a subspace of large dimension which does not intersect the singular variety of of G above QP. The other way around. Just is 0. And then we can combine that with a result which was proved by different people, but I think Trevor Woolley has the strongest quantitative statement. And then one says, and this is still a large dimensional subspace, and one can find a non-zero p-adic solution in that. So there exists, say, an X star in M. X star is non-zero, and it's a solution. So it's a p-adic solution. So if you put this together, because of the first, it's a p-adic non-singular, non-trivial solution, because we choose a subspace which doesn't have any singular points, because the singular variety has large codimension, and in that subspace, which it has still large dimension, one can find a non-singular solution. And then one has to work to find a solution such that no coordinates are also equal to 0, because we need eventually ZP cross to the S, because eventually one prime solutions. And then that one can do by looking at all the p-adic zeros near this one, by the p-adic implicit function, that's an analytic manifold. And if that would be contained in a coordinate hyperplane, then by base change, the same would be true in C, but we already removed that possibility in the cleanup process. So just without, I don't have time to explain this much further, but there exists, let's call it XP, which such that XIP, XPI is non-zero for each I. And this is in, since it's homogeneous, QP or ZP, ZP to the S, and non-singular. And that's all we need to do the scaling, the last step of the argument. Okay, so maybe I can put here the scaling of the system. Okay, so now for each P, we have this XP. And if you look at the i's coordinate of XP, it's a non-zero p-adic number. So it is of the form some power of P times some unit. Cross. Now, then we can construct the scaling factors yi. So define yi simply the product of all these factors for all small primes. So this is the small prime region. The large prime region, we have no problem. So just take the product of P to the EIP for all P less than equal to Pf. And then notice that you can write yi as P to the EIP for a fixed P times some Ni, where this is also a p-adic unit, because the product of the other primes are p-adic units which are different from P. So okay, so once we are there, then this implies that XIP can be written as yi times, now let me not confuse the end of the argument. So xip can be written as yi times wipy because this was a unit, and this is a unit as well. So you can just divide by that. And then where we are. Now let's look at define the scale system. And the whole point is, if we define the scale system, let's say gy, let's call the coordinates v1, vs to be g of y1 to be equal to v1, ys, ws, then this means that since xip was a solution, that this system has a solution for each p in zp cross to the s, because this is how we constructed the whole thing. So it has a solution w p in zp cross to the s, which is non-singular. Because x of p was a non-singular solution. And then the scaling doesn't change the rank of a system. If you just scale each variable, you multiply the determinant, it's a non-zero number. So these Vp, the coordinates Vip, is also a non-singular solution. But at the same time, it consists of coordinates like p-adic units. So exactly has these properties. And finally, one can just now apply the prime solution theorems for these systems because we have all the conditions. Each block has large rank, has non-singular solution in ZP cross to the S. So there are a lot of solutions of that system, and each solution of that system gives an almost prime solution of the original system G, which gives a solution of F, because we did not increase the solution of the zero set. So the final argument is basically just this in. So basically, it is just to finish the result in the proof of theorem M. Is basically the following. So G has high rank non-sinc local solution. And you have to work a little bit in R, but that's also not hard to show. That's very used that the system has all degrees. So then the prime solution theorem implies, let's say the number of q's in P to the S, such that G by Q equals 0. And let's say Q less than equal N over P's by I is bigger than equal than a constant depending on G times N to the S minus the total degree of the system G over log N to the S. And then writing Xi equal Yi Qi, we get Gx equals 0, which implies Fx equals 0. So we get a lot of almost prime solutions. Theorem. That's basically, yeah. Okay, so it's basically just constructing a scaling, and the main difficulty after regularizing the system, the main difficulty is playing between the two ranks and finding this mod P arguments, finding non-singular solution, unit solutions for the different primes. Okay, thank you. Bye.
Questions about? Any variables?
So basically, actually, all the thing depends on the regularization. Unfortunately, this regularization is a double induction, and it gives a power number of variables. If, well, I mean, power in terms of the degree. So the height of the tower is proportional to the degree. I think it's a system of just quadratic equation, R quadratic equation, then this regularization gives something like a double exponent, or something like 2 to the 2 to the R, for the number of variables.
Schmidt actually got it wrong. So he had a tower which was proportional.
Oh, already for.
In fact, if you do Schmidt's analysis carefully, you find that it's more like an Ackermann type function.
For high degree.
So the number of exponentials in the tower is a number of exponentials which are also iterated, and so on.
I mean, this.
That's because when you perform the Schmidt reduction, which is the regularization,
Yeah.
the equations which might decompose as
Yeah.
subsystem of equations don't necessarily occur at the highest degree in Schmidt's argument.
Oh, in his argument,
They can occur at the lowest degree.
Oh,
Maybe
yeah, he does something to raise the degree always multiplied by I don't know exactly, because for the regular element you don't, I mean for the regular VUSD you don't need it. You can start with the highest degree and that generates a bunch extra on the lower degree. You only keep those degree points and then you go lexicographic order in each degree, so you get this double.
But it could be that the decomposition occurs at the lowest degrees. Now, as you said, I mean, you could increase the lower degree equations to the higher degree, but then that's fatal to the argument.
Yeah.
So it could be that the decompositions always occur at the lowest degrees, and then that depends on the number of high degree equations as well. So it turns into this Ackermann type function.
Yeah.
And so in fact, it's more efficient for the existence proofs to follow an earlier argument of Birch from 1957, which is what I did in the 90s sometime. And you still get an Ackermann type function, but somehow you say the log in the number of iterated exponentials that you have.
Yeah, but Birch does not give you a bound on the number of solutions, right? No, not in this form, that it S minus just a constant, which depends on the R. Yeah, because it already goes into smaller and smaller subspace.
Yes, but it somehow boils down to the same thing. It's bound in this D sub G type function. So this D sub G is kind of
D sub G is basically depends essential number of equations. We don't increase the degree remains fixed because you never increase the degree, but you increase, of course, the number of equations hugely. Yeah, so that's the setback of all forms of regularity lemmas in graph theory, for polynomials. Of course, the graph theory is a little, let's say, more complicated. If you use a strong form, that you get some huge bounds, power type bounds.
Other questions or comments? If not, we thank our coach again. And we reconvene at 1:30.
much further I rejected it. So
I'll try.
I also sent an email to Kevin. I think it was.
But I need to convert this. Let's see.
You have to run.
Oh, okay. Oh, you'll be back. Okay.
That's why I have to run.
Right.
Mark the call. What CANT 26?
Okay.
Which might be the name.